In this video, I'm going to solve a practice question from chapter 7, question number 17, and we're going to use data file corporate bonds. So this is a quadratic regression type of question. I have the question here. In this question, we have a sample of 40 corporate bonds, and for each bond, we have the years to maturity and the yield. So corporate bonds is, I'm sure you guys know, but it's a fixed income security, which means you buy it, you buy the corporate bonds, you pay something upfront, and then it's a fixed income security, which means that every year, every 6 months, every quarter, depending on the term of the contract, depending on the term of the bonds, you guys, as the owner of the corporate bonds, you get a fixed amount of money from the issuer of the corporate bonds up until the an expiration date. So you get that money, right? So you get the fixed income from now until, from the time that you buy until the bond expires. So the time from now to the maturity or to the expiration of the bond is called years to maturity. And the yield is the net, basically the net profit, the rate of profit that you get at the end of the day by owning this corporate bond. Now, in this question, we want to develop a scatter chart, just visualize the relationship between years to maturity and the yield. We want to see if there is any relationship between these two. And then the question asks, does a simple linear regression model appear to be appropriate? So let's just go ahead and solve this question part by part. So I'm going to go ahead. So here we have a sample of 40 companies. I have years to maturity and I have yield. So years to maturity is my X horizontal axis. So first column X, and then yield, second column Y. So I'm taking this, both of them, selecting them, insert, scatter chart. All right. And I'm just gonna take it to the top of this page. I can just cut it, Control X, go up, Control V, and part A. So the answer to part A of this question, just to make it a little nicer, a little cleaner, getting rid of the grid lines, adding the axis titles. The vertical axis is the second column, yield, and the horizontal axis is years to maturity, or years simply. All right. So does linear regression seems to be an appropriate model? It actually looks, there seems to be an increasing relationship. As the years to maturity increase, you expect the yield to go up. So let me just, this is only true for this sample. So I'm gonna add a linear trend line. It looks okay, like it looks linear. We may actually have a better model if we use quadratic, because at the left side and at the very right side of this experimental region for years to maturity, most of the points are below the curve. Most of the points are below the curve. below the line, below the trend line, and at the middle range, most points are above the line. This indicates actually the need for having a quadratic relationship. It shows a quadratic type of relationship, all right? It's okay, like having a linear predicting line, but I would assume that if you add a quadratic, it would be much better. So I would say it seems that quadratic model is a better, it should be a better fit to the sample data. Part B of this question, develop an estimated quadratic regression equation with years to maturity and squared values of years to maturity as the independent variables. How much of the variation in the sample values of yield is explained by this regression model? Test the relationship between each of the independent variables and the dependent variable at 5% level of significance. How would you interpret this model? So going back to the data tab, for part B, I have X and Y, and now I need an X squared. So if I just insert column right between these two and call this one years squared, it's going to be squared of basically years squared. So B2 squared, and I just drag it down, drag the cell down. That way the formula is going to get copied. All right, so now for each year to maturity, I have years squared. All right. And again, obviously there's going to be multi-collinearity between years and years squared. But if we get p-values that are less than 5% for both of them, then we don't worry about multi-collinearity. So for part A and now part B, running a regression, running the quadratic relationship. For quadratic regression, we just need x and x squared. So we're all set. We just go to the data analysis, regression. And so Y range is going to be the yield. X range is going to be years and years squared. I have labels. Output range is going to be I just put it here on G19. I'm going to check the residual plots just in case. Yeah, okay. All right, so writing down the equation, that's always the first step. So yield equals 1.02 plus 0.46 times years plus or minus 0.01 times years squared. And for squared, you can use power 2, or you can simply type skew or squared, or just make sure that it's clearly specified that this one is squared factor of this one. All right, so now we have the equation, and we have the quadratic equation, checking the p-values, checking the necessary conditions, the residual plots. Both of them look beautiful, like we have symmetrically distributed residuals around 0, with constant variance, so that's okay. That's great. And multicollinearity, again, it's going to exist because between x and x squared, the correlation is going to be huge. So multicollinearity. So correlation between x and x squared. And just having the label here does not change anything. So correlation is 97%. 97% correlation, which is obvious. Between x and x squared, there should be a high correlation. Now, taking a look at the p-values, both p-values, I mean, I just checked the necessary conditions. I just checked the multicollinearity. I mean, you can just type for yourself, but both years and years squared are significant. They both have significant relationship with yield. What does this tell us? How do we interpret this? And again, when we have a negative coefficient for this, for the x squared factor, that means we have a downward relationship, downward graph. And that means we have a best downward relationship. I mean, by downward, I mean a downward curve, which means downward curvilinear relationship. This means there is a best x, there's a best years to maturity, a best range for years to maturity, which is in the middle of the range. It's not at the left side, it's not at the right side of the range, it's somewhere at the middle. All right, so this is really the interpretation of the relationship. All right. So the next part of this question, part C, create a plot. Wait, we're not done yet. Test the relationship between, how would you interpret this model? Yes, so we're almost done. How much of the variation in the sample values of yield is explained by this model? How much variation is explained? That's just the definition of R squared. So 66.8%. So 66.8% of total variation in yield is explained by this regression model. All right. Next part, create a plot of the linear and quadratic regression lines overlaid on the scatter chart of years to maturity and yield. Does this help you better understand the difference in how the quadratic regression model and a simple linear regression model fit the sample data? Which model does this chart suggest provides a superior fit to the sample data? So if I go back here if I go back on my scatter chart, I still have my linear trend line. If I just add the equation by right click, format trend line, add equation, display R squared, and just show it here. maybe down below. Yeah, all right. So this is for the linear equation, and I have the R squared for that. Now I'm gonna add another trend line. If I just click on the graph one time and then right click on one of these points and add trend line, it's gonna add a different trend line. And it's gonna allow me to change it to polynomial with the second order, right? Or you can add it from design tab, add chart element, trend line, and just maybe you just add another linear and then change it to polynomial, or yeah, so that's definitely how this works. But I'm just gonna make sure that I'm now clicking on my quadratic or polynomial with the second order, which is the same as quadratic regression, and make sure to display equation and display R squared on top of it. And I'm just gonna make it a little larger. All right, now comparing these two models, the linear model and the quadratic model, which one would you think that provides a better estimation? As you can see, by adding one factor, the R squared has jumped for 14%, which is a really significant improvement in R squared, in the power of the model in terms of explaining the variation in Y. So by adding one variable, R squared has increased by 14%. And we already know that both X and X squared are significant from here, from the p-values. Both of them have p-value greater than, less than 5%. So both of them are significant. Both of them are significant, and R squared has jumped from 52 to 66%, 67%. So I would definitely go with the quadratic model by making it a little more complicated, by adding one more variable that is significant. The R squared goes up by 14%. All right, so let me just get back to the question. Create a plot. Does this help you better understand the difference? Yes. Which model does this chart suggest provide a superior fit to the sample data? Of course, so this would be the answer to part C of the question. And it seems that quadratic regression is more powerful, or is preferred, simply because by adding one more significant variable, R squared increases from 53% to 67%, increases by 14%, which is significant improvement. So quadratic regression is a better model because by adding one more variable, which is significant, The variable is significant because its p-value is less than alpha. By adding one more variable that is significant, its p-value is less than alpha, r squared increases by 14%. So we just make it a little more complicated, but the reward is great. So I just merge this. All right. So that's the answer to part C of the question. And then the last part, what other independent variable could you include in your regression model to explain more variation in yield on other than years? So this is now your opportunity to go ahead and do some research on corporate bonds and understand what factors may affect the yield of a corporate bonds. Factors like quality rating or risk rating of a corporate bond, the company who issues the bond, interest rate, the size and industry of the company, and anything else that it can affect the yield of a corporate bond.